Hey everyone, today we are learning about section 7.1, integral as net change. Hopefully some of this will sound familiar for you. So let's get started. So the first thing we want to remember is the difference between displacement and total distance. So displacement is the change in distance. So I start here, go to the left 10, go to the right 5. My displacement is 5. Versus total distance is the actual distance traveled. So I start here, go to the left 10, come to the right 5. That's a total distance or an actual distance traveled of 15. So in the world of calculus, we want to remember that v of t represents the velocity, so movement of the object. Usually we think of it on a line. And so we have two formulas to remember for this. The formula for displacement is just the integral over your time, so from A to B, of the velocity. So this would give you that I moved 10 to the left and then 5 to the right, and it will give you that difference of 5. Now, total distance then needs you to take into account the absolute value over that distance, over that time, excuse me. So the integral from A to B of the absolute value of the velocity. Now, that sounds easy enough, except for if you don't have a calculator. So sometimes what you need to do is take your function and split it up. So let's say that the graph from A to C, or the function from A to C, is positive on that time interval. Then it becomes negative from C to B. So now what you need to do is separate it into two integrals so that you can take the second integral, which is negative, and make it positive. So you would do this when either you don't have a calculator to work with, or what the function is you're working with is too hard to evaluate using an absolute value. Or just because maybe you don't want to mess with absolute value and you like separating it into integrals. So the first thing we're going to do is we're going to work with a graph of a function that has some stuff labeled on it. So here's your graph, and this is the graph of a particle that's moving along the x-axis from time equals 0 to time equals d. The initial position, always important to remember, is 5 in this particular problem. This graph shows the velocity, and it has some areas in each of these little regions. So we want to list out some things. So when is the particle moving to the left? Well, it's moving to the left when the graph of the velocity is underneath the x-axis. So it's moving to the left from time A to B and from C to D. Okay, it's moving to the right then when the graph is above the x-axis. So we have two regions for that as well. Moving to the right from 0 to A and from B to C. And then stopped would be all of the times when it's changing direction. So it would be stopped when it's going, changes from left to right or from right to left. So it's stopped at the specific times of A, B, C, and D, which I guess I could also include 0 in the mix here because it's changing there as well. And I think my interval was closed. I can't even remember if my interview, it doesn't even matter if the interval is open or closed. It is changing direction at 0 and D, but if it were a closed interval, if we were not going outside of that interval, then we would we wouldn't include those endpoints. All right, so now we are going to talk about the displacement of the particle in comparison to the total distance over each of these windows. So let me scroll down so I can see the whole graph here. So the displacement from 0 to A, that's the first time window that we're interested in. So the displacement is just 6. And the total distance in this case happens to also be 6 because we started off at 0 and went to 6. We didn't add anything or subtract anything. All right, from 0 to B, I went to the right 6 and then left 2. So my displacement would be 4. So subtracting them, but the total distance will be 6 plus 2, which is 8. Hopefully this all sounds familiar. From 0 to C will be 4, add on that 3, so that'll be 7. And the total distance will be 8, add on the 3, which is 11. And then the displacement, the final displacement from 0 to D would be to subtract the 16 that's below the x-axis here. So 7 minus 16 is a negative 9. And then we're going to add 16 onto 11, and that becomes 27. Okay. The next thing we're going to talk about is the position of the particle at each of these times. So thinking moving left and right, but also thinking about the fact, if you remember, that the initial position of the particle from the first screen was at time equals 0, the position is 5. So then the position at time A would be 5 plus 6, which is 11. And then now we're moving backwards 2, so 11 minus 2 is 9. Moving to the right 3, this would be 12. And moving to the left 16, this would be negative 4. So you're thinking along the x-axis, we have started at 5, then to the right, then to the left, then to the right, then back to the left. Okay, next. Now we're going to do a word problem, kind of a word problem, basic problem here, but it looks like a word problem. So it says for problems 4 and 5, let me go back so you can actually read what it says, sorry. For problem numbers 4 and 5, the function is a velocity in meters per second, moving along the x-axis, so same information. It says use analytic methods. That means we want you to do some like algebra, calculus with algebra. We're going to figure out 3 things. When the particle is moving to the right, left, and stopped, find the displacement, and find the total distance traveled. Okay, so 2 problems here. This is the first one, number 4. So in order to do this one, this is the derivative, don't forget. So I'm going to set the derivative equal to 0 because that is how I know left, right, stopped. So I'm first going to factor out a 6, and this gives me t squared minus 3t plus 2. Then I'm going to factor that remaining part, divide by 6, factor what's left over, and I have t minus 1 and t minus 2. I'm going to do a number line evaluation of the velocity. Starts at 0, ends at 2, because that is what my original bounds were for the problem. And I have that 1 in the middle. Okay, so between 0 and 1, if I substitute values in here, I get the velocity is positive. And between 1 and 2, the velocity is negative. So therefore, the object is increasing, decreasing, or moving to the right, moving to the left, if you want to think about it in terms of what we're doing right now. So it's moving to the right from 0 to 1, moving to the left from 1 to 2. All right, so now I want to figure out the displacement and the total distance. So kind of think of this stuff that I just did here, kind of previous stuff that we did earlier in the year, but now we're moving on to using the things that we did in the last chapter. So we are going to integrate this function from 0 to 2. That will give me my displacement, and then I'm going to break it apart and integrate it separately so that I can find the total distance. All right, so from 0 to 2 times 6 out front, and then I am doing t squared minus 3t plus 2 dt. I'm going to show you the steps, but I'm not going to spend a lot of time on them because I know that you could do this on your own. So stop the video if you need time to actually figure this out yourself. So this is 6, and then it is t cubed over 3 minus 3 halves t squared plus 2t from 0 to 2. When I do all my substitution and simplify everything out, I get an answer of 4. So like I said, I know you can do this calculations yourself. Pause and actually figure it out if you need to believe me, I guess. Okay, so now because I'm not using my calculator, I'm going to go ahead and split this into 2 integrals. So I'm going to put a 6 out front still, and I'm going to integrate from 0 to 1. I know that's when it's moving to the right. So that integral will be positive. And then I'm going to integrate from 1 to 2, same function, because I'm not changing that. So let me fix that. I just want to make it the opposite of what it is. All right, so I also get the same antiderivative, and part of some of the values I'm substituting in are the same, so it doesn't really require that much extra work. So this is still the same integral, t cubed over 3 minus 3 halves t squared plus 2t. And this is being evaluated from 0 to 1. We already know that 0 is 0. And when we substitute 1 in, we get a slightly different answer than I got when I was working with the 2. And then I'm going to put this in parentheses. Same antiderivative. And now I am evaluating from 1 to 2. And I will have already gotten an answer for the 1 from this part of the problem, and the 2 I would have gotten an answer from above. So when I simplify the whole thing, I do believe I get an answer of 6. Now, please let me know after you try the video if you catch any mistakes so that I can go back and fix them. Okay, moving on to problem number 5. I am not actually going to work the whole problem out with you because, again, I know you know how to do these problems. It's the same directions as before. So the directions are still asking for you to find where it's going to the left, going to the right, and it's asking, of course, for stopped, and then displacement and total distance. So the main thing we need to know is when it changes from left to right so that I can reset up my integral to go from change the bounds. Okay, so I'm just going to quickly give you some of the answers that you get. And again, stop the video and figure it out yourself if necessary. But I am going to go over the trig because I know sometimes that's a problem for everyone. So this is the derivative. So the derivative gets set equal to 0 to figure out where the particle's changing direction. So I get sine of 3t equals 0, and I need to know where sine equals 0. Well, sine equals 0 at 0 and pi. And I do choose the pi, even though pi is not in this bounds, because I know when I divide by 3, that's going to give me a value that is between 0 and pi over 2. So it gives me pi over 3. I always take a couple, like at least one extra, even if it's outside of the bounds, just to make sure that when I divide, I don't lose an answer. Okay, so when I do a number line test, what we're going to find is that the particle is moving to the right from 0 to pi over 3. And it's moving to the left from pi over 3 to pi over 2. And you would do this with a number line test, okay? That means you need to do it. The first problem you're going to integrate for the displacement, just normal, from 0 to pi over 2. I would put the 6 out front. I would write it as sine of 3t, and then do all of the stuff that I know you all know how to do so well from the previous chapter, and determine that when you evaluate from 0 to pi over 2, the displacement will be at 2. Okay, and then to do the total distance, still have the 6 out front. Now you're going to have two integrals, or you're going to use absolute value. We're going to go from 0 to pi over 3, and then we're going to subtract the answer I get from pi over 3 to pi over 2. Okay, so I'm not even going to write it all down. Once you put this into your, once you work this all out or put it in your calculator, if it's a calculator question, you should find that the final answer is 6. So again, if you're not getting the same answers as me, please let me know and I will recheck my video. All right, now we're going to move on to a couple of word problems, which is probably the stuff I think is a little more confusing for everybody, just because we're not, don't always read things carefully, and they just make us a little more anxious. So I'm going to read the problem. It says the rate at which your home used electricity is measured in kilowatts. If your home consumes electricity at a rate of 1 kilowatt per hour, you will be charged for 1 kilowatt hour of electricity. Kind of not really that necessary, even to understand that in this problem. Okay, so here's the actual question, I guess. Suppose that the average consumption rate for a certain home is modeled by this function, where C of t is measured in kilowatts and t is the number of hours past midnight. Find the average daily consumption for this home measured in kilowatt hours. Okay, so you want to figure out how much was consumed over 24 hours, and then divide by 24 hours. So, what you need to do is to figure out how much was consumed, you are going to integrate over a 24-hour time period. So, from 0 to 24. So, you're going to integrate this, and this could be done by hand. Oops. But I don't know that that's necessary. I think you could probably put it, I think this would probably be a calculator question. Make sure I got all the right stuff here. 2.4 sine pi t over 12 dt. Okay. But then I need to divide by 24 hours so that I can find the average daily consumption, meaning I want to figure out how much I'm going to get um, in one day. Okay. So I'm going to divide by 24 or multiply by 1 over 24. And notice this should look a lot like your average value formula from, I think that was chapter 5. Okay, so kind of similar to what we did in chapter 5. And when you evaluate this whole thing, you should get that the average consumption is 3.9 kilowatts per hour. Okay, again, do it yourself. Make sure you believe what I did. Check to make sure I didn't make any mistakes. And move on to the next problem when you're ready. Okay, last problem's typing looks funny. Sorry about that. So this one is problem number 7. And it says that a pump is connected to a generator that operates at a varying rate depending on how much power is being drawn from the generator to operate other machinery. Kind of one of those things that reading it's helpful but not necessary. The rate in gallons per minute at which the pump operated is recorded at 5-minute intervals. So that's probably important to know. At 5-minute intervals for 1 hour as shown in the table. Estimate the number of gallons that were pumped in that hour. Okay, so you're trying to figure out um, the gallons that were pumped. So this is really an integral that we're doing. And again, going kind of back to chapter 5, we would have done this. One of the ways we would have done this would have been to use like one of your RAM methods or your trapezoidal method. So I went ahead and actually did that already for you. So I used LRAM, and I just used obviously the intervals that are here. LRAM gives me 3295, I hope. RRAM gave me 3300. So then we know that the trapezoidal method would have given me 3297. Sorry, I couldn't read my own handwriting. 0.5. Okay, so it's probably a pretty good estimate, but we do have ways to maybe make it maybe a little bit of a better estimate. Still not 100% necessarily accurate, but another thing that we can do is to use your calculator to come up with a regression. Okay, so if you were to go and grab your TI, and I'm not sure if you guys learned how to do regression on Desmos. If you didn't, maybe we will talk about how to do that on Monday. But you're going to go to your TI and you're going to use sine regression because this turns out to be a sine curve. So you would put all of the data in. So you're going to do your list 1, list 2, and then do a sine regression. Make sure that you are in radian mode and that you use the normal period of 2 pi. Okay. All right, so then what I would recommend you do is after you put the data in, and sorry, I would do that, but I don't want to make the video any longer by me just showing you how to put data in. I know you know how to do that. So put the data in, look at the table, sorry, look at the graph of it, and then try and do your sine regression and put the sine regression on top of the data to make sure it makes sense. Because if you don't have the right period or you don't have it in the right mode, it won't match. And so that'll tell you that you did something wrong. So what I came up with. I believe, and I'm starting to doubt myself for a second here. I believe that this is what you're supposed to put in there, but maybe you don't have to put anything. I'm not even sure. So maybe if you just leave it undefined and just put nothing, you might be fine. So try it both ways. All right, so this is what I came up with as a function. So I came up with, I'm rounding here, but if you put it into your calculator and store it in y1, then you would not have the rounded version, which will be perfect for what we're going to do next. So I got approximately 4.045 sine of 0.144x minus 0.061 plus 88.953. And again, this is my rounding. Leave it in your Y1 in your calculator the way it is. And then when you graph it, you can do this awesome thing where you, right on the graph, you hit calculate and ask to integrate. And you're going to integrate from 0 to 60 because this was over 60 minutes. And you're going to integrate Y1 and it will show you right on the graph what it is integrating. And when I did that on my calculator, I came up with 3583.851. And I think this is probably a better representation of what the actual number of gallons were in this home. If you have questions about how to put this in your calculator, make sure you ask tomorrow in class. Otherwise, we are done.